You might be taking a physics class, and if so, you might meet this particularly insidious problem. It'll just come up and say, "Hey," to you, and you'll look at it and you'll be like, "What?" And it'll say, "Hey," and then you'll read it, and it'll say, "Newton fires a potato cannon or spud gun at an angle of 25.0 degrees from the ground." So here he comes, and he's gonna go, and the potato's gonna fly out, and it's going to travel 301.5 meters before landing. The question then asks, how high up did it go? Such a simple problem. Well, let's first do what you would absolutely not want to do. So you might be thinking, oh yeah, you can draw the velocity and it's like that or something, and there's this 25-degree angle, 25-degree angle, there we go. And I've never actually done this, but a lot of my students want to do things like this. And the distance that it goes is 301.5 meters in the x direction. So the distance that it goes in the y direction is probably related by tangent, right? This is the adjacent side, that's the opposite side. I could write down that tangent of theta is opposite over adjacent. If I'm trying to find the opposite, what am I going to do? I'm just going to take that adjacent side, I'm going to take 301.5 meters, and then I'm going to multiply it by the tangent of 25 degrees. And that's going to be so wrong. This number here is so wrong because guess what? Our potato doesn't fly in a straight line. That's crazy. Think about what you're saying. The potato's just going to go up, 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 higher and higher. It can't land then. It lands. See? It can't land if it's not accelerating downward. It's probably going to be doing something like that. And the height that you want is right here. So please, 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 please remember that things accelerate when they're in free fall. Shoo! All right, so let's address this problem in a proper way. Not like that. Newton fires this potato can. Here's what I'm going to do. I'm going to draw draw a sketch, and we can think a little bit about what we know. Here's our sketch of what's happening. Ground and parabolic motion up above the ground, and this distance here, delta x, I'll call it delta x total, is the distance that the potato has traveled, and I know that to be 301.5 meters. And then I'm interested in finding, see, let's do this like the focused attack way. I'm interested in finding delta y max, which is also delta y when it's at its peak. So I'm going to call that delta y top. I'm going to have tops and totes so that this can be maximally confusing. This is the delta y top, that's delta x tote. But what about like how far it's gone in the x direction when it's at its peak? I could call that delta x top. That's this distance right here. That's just how far it's gone in x when it gets to its peak. And what I notice immediately is because the symmetry of this parabola, delta x top equals 1/2 delta x tote. All right, so I'm taking this total distance and I'm dividing it by 2. So in this case, it turns out to be 150.75 meters. No sig figs because we're in the middle of the problem. Also, there's something magical happening up at the top here. Maybe you can think of what that is. What happens at the top of a projectile's path that's incredibly important? Well, it doesn't stop accelerating, but it stops going up and it starts going down. That's the essence of being at the top of something. So I'm going to say at top, velocity in the y direction equals 0. Let's establish x and y. Let's be honest about this. There's y, there's x. And at the top, vy equals 0. So I could also say something about t top. How do you think t top is related to t total? In the same way as delta x top is half of delta x total, I think I can argue that t total divided by 2 is equal to t at the top. And so there's this beautiful condition that the velocity in the y direction is 0, and we're going to use that several times in order to solve this problem. So that's our picture of what's happening, and there's also this other thing I want to do at the very beginning of every projectile problem. I probably should have done it earlier because I really do want you to do this immediately. There's this initial velocity vector. I want you to draw it. The initial velocity vector is like that, and then I want you to resolve it. We've got x and y like that, so I can draw a dotted line in the x direction. and a dotted line in the y direction. I know that x and y are normal to each other, so this is the initial velocity in the x direction. This is the initial velocity in the y direction. But wait! Oh shoot, Doc, we don't even know what that is. The hypotenuse is a variable. Does that make you uncomfortable? It makes me uncomfortable. 25.0 degrees is the angle right there, but we're just going to write down the variable right here. V naught in the x direction is simply V naught times, let's see, adjacent, that's so it's cosine of the angle, and this is V naught times the sine of the angle. So whenever I have an equation that asks for V naught in the y direction, I can write V naught sine theta, and similarly, if I have an equation for V naught in the x direction, I'll just write V naught cosine theta. Now, the reason we separate these is because one of them's changing and the other one's not. And I'll leave it to you to figure out which one of these is changing and the other one is not. Next page. I want to do this, as I said, in a direct and focused way. I want to find an equation that has delta y at the top, which is what we're trying to find. And we know, I guess we just know delta x total and we know theta. So we can record that we know those things, but we'll kind of put them in a box, and I'm not going to plug in any numbers until the very, very, very end. Actually, I'm never going to plug in numbers. That's up to you. But I want to use the fact that at the top, the final velocity in the y direction is 0, right here. So I'm looking for an equation that has delta y at the top and has the fact that the final velocity in the y direction is 0. So the classic doesn't have final velocity in it, but look at this, the definition of acceleration, that's got final velocity in it. Oh, but it doesn't have delta y in it. Now this one has final velocity and delta y, but it's got time, and that makes me uncomfortable. I'm going to go to a tale of two scores. Tale of two scores has all that I need, and I'm going to use it at the top. So first I write down a tale of two scores. It says the final velocity in the y direction. Square is the initial velocity in the y direction. Square plus 2 times a in the y direction times delta y. At the top, check it out. I'm going to have to write a little bit smaller. At top, we get 0 equals the initial velocity. Now, I'm going to plug in what the initial velocity in the y direction is. I'll remind you that the initial velocity in the y direction is this business right here. It is V naught times sine of theta, but I'm supposed to square it, so I'll square the sine theta and I'll square the V naught. All right, and then I'm going to add on 2ay delta y. And then this delta y, because I'm thinking about at the top, this delta y is going to have to be labeled delta y top. Lo and behold, that's the exact variable that we want. So I'm going to subtract this term from both sides and then divide by 2ay, and I'll get delta y at the top. This will be lovely. Watch this. Delta y at the top equals negative v naught square sine theta square divided by 2ay. This seems to be saying, though, this might make you a little bit uncomfortable. Sorry about my throat. Because it looks like delta y at the top is a negative number. Is the potato indeed below the ground? Well, you figure that out. I'm not going to answer that question for you, but I want you to notice that this equation is worthy of a flower pot. Let's make it an orange one, because... You want an ice cream cone too? No, I'll give you a star and an exclamation point. If we know everything in here, we can turn in the answer. V naught square, shoot, that's the only thing we don't know, because we know theta and we know acceleration in the y direction. Oh, I should put that in this little box. Some other things that we know. Acceleration in the y direction, everybody knows that. Okay, Primrose, what are we gonna do next? Let's go to green. We need to go on a side quest to find V naught. So, as soon as we find V naught, we'll come back to this equation though. Here's how my side quest works. I'm interested in looking at the x direction because this was some y direction work. In fact, there's only one equation in the x direction, and it says how far you've gone in the x direction is how fast you've been going in the x direction times the time that you have been going. And I'm going to, I guess I'm just going to say at the top, this is kind of a little bit of a silly statement, but at the top, delta x top equals V naught, and instead of writing V naught x, I'm going to write V naught times the cosine of theta, because those guys are equal. So V naught cosine theta times delta t at the top. Now, this equation can't work for us yet because I need to figure out what time is. So I'm going to go to a third equation to do that, but I'm going to put this guy in a little box so that we can revisit it when we need to. The third equation is in fact the definition of acceleration, and I'll look at that in the y direction. And that says the velocity in the y direction is the initial velocity in the y direction plus the acceleration in the y direction times time. And at the top, see how we keep doing this? We're trying to use the top to attack this problem. At the top, we know 0 equals the initial velocity in the y direction, but I'm going to write, instead of the initial velocity in the y direction, just as I did over here, I'm going to write v naught times sine of theta. And then I have to add the acceleration in the y direction times time, but now this time is not just any time, it's time at the top. I've been putting in deltas and dropping out deltas all day, sorry about that. I will not put a delta in for time, I'll just say that that's time right there. All right, good. So notice that we've got an equation here for time at the top and another equation here for time at the top. What's the other variable in here? We got AY, that's a known. We got theta, that's a known. And we've got delta x at the top, that's a known. And we've got V naught. See, V naught we don't know, and time at the top we don't know, but we have two distinct equations for them. And what do we do when we have two equations and two unknowns? Why, we substitute. So I'm going to plug this equation into that equation, but to do that I need to solve this equation for t-top. This equation right here for t-top, the x direction equation for t-top. Let's go pink. The x direction for t-top says t-top equals delta x at the top divided by v naught cosine theta. We'll put that in a little circle, and we'll drag that circle down here, and then I'm going to rewrite my equation. Let's continue in red. 0 equals, oh, this is infrared, very nice, v naught sine theta plus acceleration in the y direction times delta x at the top divided by v naught cosine theta. Let's check this equation. How you doing, equation? This is a combination of x and y direction stuff, so it's kind of complicated, but we've got v naught, which we don't know. We've got theta, which we do. Ay, we know. Delta x at the top, we know. Theta, we do know. V naught, we don't know. Ooh, there are two things we don't know, but they are the same thing, and we just don't know them. So let's get v naught on its own. The problem is there's a v naught in the denominator, and that freaks out everybody. I don't like that one bit. So I'm going to multiply both sides by v naught. That means that, whoa, if I multiply both sides by v naught, I'm going to put v naught over here, and it has to multiply both these terms. V naught times 0, that's still 0. 0 equals v naught squared times sine of theta, right? Because I had to multiply by v naught, plus acceleration in the y direction, delta x at the top, divided by, wait a second, divided by cosine theta. See, I don't have to divide by v naught anymore because I was multiplying by v naught, which was the entire point of that exercise right there. Now I'm going to subtract this term from both sides and divide by sine theta. Watch this. As I subtract this term from both sides and divide by sine theta, we'll just see what happens. I get negative ay delta x at the top divided by cosine theta. Now that step I just did was pretty slick. See how I extended the division right here? I need to remind you that a times b over c is a times b over c. So I don't care where I put that line in. If you don't know this, you should write this on a little scrap of paper and eat it tonight. Just before bed, just eat that equation and then you will know and believe. So this is, well, we have this stuff left over here. I was subtracting that from both sides. I was also supposed to divide by sine theta, so I'll divide both sides by sine theta, and I get v naught squared. I don't want v naught squared, so I'm going to actually scroot both sides. Watch this. I'm going to scroot both sides. I get negative ay delta x at the top divided by, I'm going to switch sine and cosine because I like to say sine theta, cosine theta. It's more fun to say than cosine theta, sine theta. Try it sometime. It's really different. Then I screwed it. Are we screwing a negative number? What? Ah! Maybe we are. Maybe we're not. You figure that out. Now, we have an equation for V naught in terms of all stuff that we know. This is negative 9.81 meters. Oh, it's negative times negative, so it's going to be positive. That's nice. This is 150.75 meters. Theta is a known number, 25 degrees in this problem, but we're not going to plug it in. We're going to leave it in this raw, beautiful form. Check this out. This is the equation for V naught. All I have to do is put this sucker in a circle. It's going to be an infrared circle, and look, it's not even complete. And I'm plugging it in right here. Our side quest is complete. Now all we have to do is take this and plug it into there, and I'm going to need a little bit more room. So I've got an equation for delta y at the top, and I'm going to write it again right here. Here we go. Delta y at the top equals. Now I'm supposed to put a minus sign down, and then I'm supposed to score all this business right here. So I'll show that step. I got all day, right? You guys, you can skip it if you're getting bored. Negative ay delta x at the top divided by sine theta cosine theta. And then this thing is supposed to be square. And I'm multiplying that by sine theta, that quantity square. See that? That's right there. Those are the same thing. Then I'm supposed to divide the entire thing by 2a sub y. Wow, that looks kind of nasty, but luckily I'm squaring a scroot, so it gets a little bit better. And then this stuff is in the denominator, so I'm going to write it down in the denominator in the next line. I get negative ay delta x at the top times sine of theta sucker square, and then my denominators include 2ay and sine theta and cosine theta. 2ay sine theta cosine theta. Lovely! I mean, yuck! Look, minus times minus is plus. Ay cancels ay. Sine theta's down here. There are two sine thetas multiplied together up there, so I get sine theta canceling that square right there, and this becomes a much simpler, let's write it over here, delta y at the top is now just delta x at the top divided by 2, see delta x at the top divided by 2, and then I'm multiplying that by another fraction, sine theta over cosine theta. And my people may remember delta y at the top, what sine theta over cosine theta is. That's delta x at the top divided by 2 times the tangent of theta. Now look where we've been, people. We started by drawing ourselves a nice sketch. We understood what was happening. We know delta x at the top is 150.75 meters. We know theta is 25 degrees. Then we did an enormous amount of algebra using not 1, not 2, but 3 kinematic equations, 2 in y and 1 in x, all of them plugging information about it being at the top, at the top, at the top, at the top. See all those at the top statements right there? Then we finally plugged everything back together and we got this beautifully elegant equation. This is typical in physics. Things get nasty. This is nasty. This is gross. But then look at the beauty at the end. This is the tangent of theta. And it's actually got some similarities to the horrible wrong approach that we crumpled up, because there is a tangent of theta. But how to get that geometrically? Well, I give that to a challenge. I give that to you as a challenge. Try to figure out that geometrically, because that's kind of nasty. But look at the beauty that comes out after the nastiness. And this way, we know, let's see, if check the units. Tangent of theta has no units, right? 2 doesn't have units. But delta x at the top has units of distance, and this has units of distance. So it's really a fantastic problem. And we find that the sucker has gone up 35.1 meters or so. Try it out. Goodbye. So that this can be maximally confusing, this is the delta y top, that's delta x tote. But what about like how far it's gone in the x direction when it's at its peak? I could call that delta x top. That's this distance right here. That's just how far it's gone in x when it gets to its peak. And what I notice immediately is, because the symmetry of this parabola, delta x top equals 1/2 delta x tote. All right, so I'm taking this total distance and I'm dividing it by 2. So in this case, it turns out to be 150.75 meters. No sig. You might be taking a physics class, and if so, you might meet this particularly insidious problem. It'll just come up and say, hey, to you, and you'll look at it and you'll be like, what? And it'll say, hey, and then you'll read it, and it'll say Newton fires a potato cannon or spud gun at an angle of 25.0 degrees from the ground. So here he comes, and he's gonna go And the potato is going to fly out, and it's going to travel 301.5 meters before landing. The question then asks, how high up did it go? Such a simple problem. Well, let's first do what you would absolutely not want to do. So you might be thinking, oh yeah, you can draw the velocity and it's like that or something, and there's this 25-degree angle, 25-degree angle, there we go. And I've never actually done this, but a lot of my students want to do things like this. And the distance that it goes is 301.5 meters in the x direction. So the distance that it goes in the y direction is probably related by tangent, right? This is the adjacent side, that's the opposite side. I could write down that tangent of theta is opposite over adjacent. If I'm trying to find the opposite, what am I going to do? I'm just going to take that adjacent side. I'm going to take 301 points. Newton fires this potato can. Here's what I'm going to do. I'm going to draw the draw a sketch, and we can think a little bit about what we know. Here's our sketch of what's happening. Ground and parabolic motion up above the ground. And this distance here, delta x, I'll call it delta x total, is the distance that the potato has traveled, and I know that to be 301.5 meters. And then I'm interested in finding, see, let's do this like the focused attack way. I'm interested in finding delta y max, which is also delta y when it's at its peak. So I'm going to call that delta y top. I'm going to have tops and totes, 0.5 meters, and then I'm going to multiply it by the tangent of 25 degrees. And that's going to be so wrong. This number here is so wrong because guess what? Our potato doesn't fly in a straight line. That's crazy. Think about what you're saying. The potato's just going to go up, 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 higher and higher. It can't land then. It lands. See? It can't land if it's not accelerating downward. It's probably going to be doing something like that. And the height that you want is right here. So please, 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 please remember that things accelerate when they're in free fall. Shoot. All right, so let's address this problem in a proper way. Not like that.